All right, so it's 1 minute past the hour, so we're going to start talking today about what can be a really dry and boring topic, fault tolerance, which sounds somewhat negative. We don't want to tolerate less than perfection, but fault tolerance is a very useful concept, and we can use it to our advantage, or we can use it as a concept in our design for reliability initiatives. I'm going to start with an example. The example I'm going to start with is this thing called Chaos Monkey. Now, some of you may have heard of Chaos Monkey, some of you might not. And Chaos Monkey is a wonderful example of how an organization can learn to live with faults. And Chaos Monkey is actually the brainchild of a bunch of guys and girls at Netflix, led by this guy, Greg Orzel. So I'm just going to read some quotes that Greg came up with when he's describing this weird simian, this weird ape called Chaos Monkey. And Greg said that at Netflix, our culture of freedom and responsibility led us not to force engineers to design their code in a specific way. So Netflix, as we know, is a video streaming service. And of course, there's hardware associated with data centers and data storage facilities, things like that. But a lot of what Netflix does is based on software. So Greg continues, instead we discovered that we could align our teams around the notion of infrastructure resilience by isolating the problems created by server neutralization and pushing them to the extreme. And so we created this program called Chaos Monkey, a program that randomly chooses a server and disables it during its usual hours of activity. Some will find that crazy, but we could not depend on the random occurrence of an event to test our behavior in the face of the very consequences of this event. Knowing that this would happen frequently has created a strong alignment among engineers to build redundancy and process automation to survive such incidents without impacting the millions of Netflix users. And Chaos Monkey is one of our most effective tools to improve the quality of our services. So what Chaos Monkey did was randomly disable the server in a relatively controlled environment, had a bunch of software and test engineers watching what was going on, and they said they would step in if something bad was going to happen. So if something bad was going to happen, they'd step in. Then they analyze what that bad thing is going to be. And they analyze that. Once they analyze that bad thing, they came up with more robust software code to deal with that problem. And so they ended up creating a bunch of different programs, starting with Chaos Monkey, which essentially declares a virtual instance, deletes a virtual instance, or disables a server every hour. So this is happening every hour during, let's call it normal operation. Then there was Chaos Gorilla, which is a little bit more profound than Chaos Monkey. And Chaos Gorilla would randomly take out data centers. Chaos Kong would take out AWS regions. Latency Monkey would introduce communications delays to simulate degraded networks. The Doctor Monkey was a program that looked at things like CPU load to identify unhealthy instances for further investigation. Then there's Janitor Monkey, which would automatically delete code that hadn't been used for a certain amount of time. Security Monkey would look for searches for and disables instances with known vulnerabilities. And there's Conformity Monkey to make sure virtual instances line up against a set of rules. So essentially what they were doing was they were attacking their own infrastructure. They were creating these programs to attack the very framework within which they were trying to stream videos to people like you and me. So why were they doing this? It's because they wanted to create a system that could tolerate things not being perfect. And a lot of reliability engineering, unfortunately, is premised on the perfect customer. or the perfect operating conditions, or the perfect use case. And companies who assume or have their entire business plan based on perfection don't last for long, because the reality is there are imperfections everywhere. We've all known or heard of those companies which blame the customer for their products failing. Now, customers are not inherently vandalists. They don't, when we buy a printer or a modem or a car, we're not, as a rule, deliberately trying to break it. We're just going to use it in the way we want to use it. A good example is the original mobile or cell phones, which came out initially as luxury items because they were so expensive for the rich and famous. But the people who actually took up mobile or cell phone technology first were tradespeople, because back in the day when we only had landlines, they had to go and, for example, fix a pipe at a house or repair something on a property and go back to the office to get the next job for the day. And having a very expensive cell or mobile phone allowed them to forego that trip back to the office to find out what their next job was. So the expense of that mobile or cell phone, which was brick size and not good compared to today's standards, more than paid for itself in the long run. And the companies which created those initial first generation of mobile or cell phones that were able to withstand a little bit more robust use case associated with tradespeople were the ones who did very well. The others who didn't, the ones who were catering exclusively to a boutique clientele and were hoping for perfection as they saw it in terms of how their phones were handled, did not last very long. So we're all about having to deal with imperfections. And one of the really key takeaways from today's webinar, or fault tolerance more broadly, is that improving reliability is way more important than measuring reliability. When we measure reliability, we almost have to assume a certain use case or set of environmental operating conditions or other things that we are tempted to define as perfection. And fault tolerance is a really important part of improving reliability. Fault tolerance is not easily analogous or a natural element of measuring reliability. Measuring reliability, as I mentioned, has to have those presumed environmental conditions, those well-explained human users. Fault tolerance is actually all about making sure we can adapt or be just as reliable when those assumptions are no longer valid. So we're going to go and look at a chart which I often use in my webinars, which hopefully illustrates well the strength of the product, system, or service we are building. When I say strength, I use the term strength in the context of being able to defeat challenges to our system. If we have a steel beam which is exposed to a stress, we want the strength of that beam to be higher than that stress, because if it's lower than that stress, our steel beam will fail. If we have a certain circuit board and it's exposed to a certain amount of vibration, we want the strength of that circuit board measured in terms of vibration, perhaps GRMS, to exceed the vibration stress it's exposed to. So strength is analogous to whatever metric or measure you're trying to use, and a way to describe how robust your system is. And this chart here represents the invisible mountain range of failure. You typically have thousands of ways your thing can fail, and each one of those ways has its own strength profile. So your circuit board on your consumer product will have a certain strength measured in terms of vibration profiles. That's in a wireless modem router, which has a circuit board, the casing will have a certain strength in terms of mechanical stress. The power supply will have strength in terms of how much input voltage it can endure before it fries, so on and so forth. So we have all these different ways our wireless modem router can fail, for example. And this hidden mountain range of failure is supposed to represent the strength density profiles of all of these possible failure mechanisms. And right down here, we have the stress that our product, system, or service is exposed to. This red density bell curve represents the variation in ways our users or customers are going to torture our device. You can see here that our invisible mountain range of failure unfortunately overlaps the stress that our product's going to experience. So this tells me straight away we have a problem. We have a failure problem before we even move on. Now, the reason why this is invisible is because we're looking at this from the very start of the design process. And what you're seeing here is us trying to remove that invisibility. So what we've just seen is we've seen nuggets of gold born of corporate knowledge and experience extracted from our brains through a familiar. And a familiar is a wonderful tool. And those nuggets of gold will let us know that, formalize our understanding of our system in a way that helps us improve our design. So we, for example, might have Bill, who remembers in the previous version of our pump that we had a fatigue crack at this particular flange. And so instead of having to go through the process of come up with the initial design and the prototype and test and finite element analysis, so on and so forth, we just listen to Bill. We say, you know what, thanks to that, Bill, that's fantastic information. We're going to increase the radius at that flange to make sure we reduce the stress concentration factor. We might do finite element analysis later on our first initial blueprints to make sure that the stress intensity factors are relatively low. But from the start, by listening to Bill, we've incorporated a very simple design characteristic for essentially nothing that will eliminate failures later on. Then we listen to Susan, who said, you know what, we had some cavitation issues with the pump in the previous version. And if we modify the impeller profile like this, we should eliminate that cavitation problem. Yeah, that's fantastic, Susan. Thanks for telling us that. And as we listen to these people, what happens is these invisible mountains and these invisible mountain ranges become visible. And then we implement corrective actions to improve the robustness of our design. So our mountain range, which represents the overall strength of our system, starts moving to the right, away from our typical stresses, which is what we want to have when it comes to robust or reliable systems. And that's reliability allocation. Now, this is something you can do for more complex systems, but the idea is we want to make the most challenging components of our system the weakest points, and that sounds somewhat counterintuitive. But what that also means is we want the least challenging components, the simplest components, the naturally strongest components to be the ones that we demand the most of. And by simply making sure that we have the most or the easiest reliability goals for the newest technology or new components, we don't waste time and money trying to take this brand new generation of technology or this first iteration of a new component and ask more of it than we ask of the other components that have been embedded in our system for the last few generations or models. And so we can save lots of time and money and grey hairs when we get reliability allocation into play. All it does is move our more complex components or more challenging scenarios to the left. But we still have some hidden mountains in our mountain range. We've done a familiar, we've done some reliability allocation. We've resolved a ton of problems, but we still have a couple left. So let's just say this is an electronic component. We might do something like derating, component derating, where we deliberately say, you know what, even though the manufacturer says that capacitor is rated to 8 volts, and we have an application which demands 8 volts, we're going to have a 50% derating policy, which means that I'll only use capacitors rated to 16 volts, which are more robust. And by doing that, we have moved one of our hidden mountains again to the right. So we're starting to increase the margin, increase the distance between the stress and the strength. And thank you very much, Ahmed, for that shout out from Mississauga, which is just up the road from where I am now. Okay, So once we got to this stage, there's still more things we can do. For example, we can do halt. The reason we want to do halt is because these mountains, these strength density curves don't stand still. Things degrade over time, which means that something might be quite strong at the start of its operational life, but as it accumulates damage and it gets older, it moves to the left. Things get weaker over time, which is essentially what every single wear out failure mechanism looks like. And so halt is a great approach for rapidly subjecting our system to some high but controlled stresses to accelerate the degradation of these failure mechanisms, move those strength curves to the left as quickly as possible, and look what we've got as a result. We have found what we like to call the vital few. And these vital few failure mechanisms mean that we are able to target those three weak points with a corrective action. They get moved to the right, and now we have the next three vital few weak points of our design that we need to do something about. So this is how we make reliability happen. Well, this is an example, I should say, of how we make reliability happen. We continually target the weak points of our system. That means we don't over-engineer. That means we don't waste time and money making a thing too reliable. So before I move on, are there any questions about this little sequence I've covered, how we have this hidden or invisible mountain range of failure at the start of any design process? We go through the process, use activities like Vermeer's, for example, to try and get some visibility of these mountains and this invisible mountain range of failure before we test and design and otherwise invest money into a design that needs to be changed later. Do things like derating and halts and all these wonderful things to make sure that we move this invisible mountain range of failure to the right as early as possible. Are there any questions while I take a quick breather? Any questions at all? Thank you, Maximilian. But I'm going to ask you guys a question. I've talked about derating for Vermeer's. Can anyone just in the comments box or the chat window, I should say, just throw out some other activities which you, in your experience, has achieved the similar results. Similar results to what we've just looked at so far, where we've moved our hidden, invisible mountain range of failure to the right. There's lots more than derating. There's lots more than halt. Anyone want to share their experiences about DFR activities which align with what we've talked about so far, just to get the ball rolling? Limited lubrication to a system to increase wear. You mean that that you have a lubrication strategy for the purpose of extending the wear or time to wear out, I should say, of a component. Derating aircraft engines for increased life. Lovely, fantastic. Very similar to derating the capacitor I talked about, except that an aircraft engine is a much more complex bit of kit. Some of you might have heard of sneak circuit analysis, where we look at how electric circuits can do weird and wonderful things when we least expect it, by actually examining how those circuits will operate in real life. Okay, so I've got a couple of good shout outs there in terms of activities that we can employ, I should say, to move our hidden or invisible mountain range of failure to the right. But there will come a point where we can't do anything anymore to our failure mechanisms, or at least we can't do anything in an efficient and a cost-effective way. Sorry, I got one more suggestion. Add a lock washer to prevent screws vibrating loose. That is a fantastic suggestion, Keith, and I want to really emphasize how fantastic that one is, because it's so simple. It seems almost stupid's a strong term, but we often get enamored by more sophisticated, more sexy design solutions where lock washers, nylocks, lots of really simple things we can do when we manufacture something are just fantastic at eliminating 90% of the problems we're going to experience later on. Simple is awesome. So lock washers, for example, are a great way of getting ahead of the curve and pushing that curve to the right. But once we've done all that, once we've incorporated all the lock washers, derating, got our lubrication right, there are sometimes we just can't keep pushing or asking any more of our components. Perhaps there's a space limitation, perhaps there's a cost limitation. We need to do something different. That's when we need to start tolerating faults. So if we go back to our little chart where we had all these wonderful density curves describing the different ways our system can fail. And it looks pretty good after our few activities. We've moved everything to the right, but we still have these vital few. And of course, these vital few are going to degrade over time. And the most problematic one at this stage is, in this case, a pump. Our pump represents our weakest point in our system. And of course, we know this by this stage because we've done the familiar, we've done the halt. We probably have done other things, and we should have at least started to look at the physics of failure of these vital few things that our familiar and halt came up with. And it turns out that it's going to be a pump. Pump is the weakest part of our system. And we have looked at improving the design of this pump. And now we need to do something else. We need to start tolerating the faults that are causing problems. Sorry, I got a bit ahead of myself. So the key thing about these vital few is that if we want to improve the reliability of the system, we need to improve the reliability of the vital few, which is fantastic. If we improve the reliability of the trivial thousands, the things that are already relatively strong, what we do is over-engineer. And I'm not interested in over-engineering, I'm interested in reliability. Over-engineering is not the same as reliability. So we got our weak point here. What can we do for our poor old pump, which is the weak point of our system? Well, here is our pump. And most pumps, for example, have a region of high reliability. So you will see efficiency profiles for pumps, and it turns out that most pumps, there will be this little band in the middle where efficiency is maximized. Now, efficiency is almost not analogous to reliability, but it's an indicator of reliability. That is, if you operate outside of your efficiency zone for a particular pump, you tend to put stresses on its individual parts and elements and accelerate failure. So what we can do is find a pump which has a bit more tolerance. In this case, we've replaced our pump with another pump which has a larger region of efficiency or a larger region of higher reliability, which means that for different flow rate demands, it's still going to be relatively efficient, which means we limit the stresses the parts of our pump are exposed to. And we call this variability control, where we use components that can tolerate larger variations in inputs caused by failures or faults in other components. And this is where some engineers with a forensically surgical perspective of use cases and operating environments and operating stresses can get into trouble because they refuse to accept they need to design something outside of specifications. Nope, the temperature is specified to be 13.8 degrees Celsius to 18.2 degrees Celsius. My pump only needs to work within that temperature range. That's not useful because we all know that there's going to be times, there's going to be events, there's going to be emergency shutdowns, which introduce perhaps unanticipatable environmental variations. So increasing the variability, the extent to which our components can tolerate variations in these scenarios inherently increases reliability. So this is the first way we can tolerate faults, by introducing variability control. Then we can do things like have a regulator which protects our pump from upstream faults, like pressure spikes that can come down that pipe and really ruin the day of our impeller, for example. So this is called fault containment, where if something goes wrong somewhere else, we make sure that fault doesn't, again, ruin the day of our pump. And there are plenty of other examples besides regulators. And what we want to do is we want to mitigate the effect of faults in other parts of our system as it relates to the failures of this part of our system. Now, remember, a fault is not a failure. A fault is a situation or an element or a defect or some event or some physical characteristic which can initiate a failure mechanism, which will then, of course, lead to failure. So if we want to stop faults propagating to failure, and one way of doing that is containing faults where they lie. This is the second approach to tolerating faults. Now, a third approach deals with scenarios where something is starting to go wrong. Now, again, a fault of itself is not failure. So when we do identify a fault, if a fault occurs, we want to identify it and then understand that we have a fault in our system before that fault propagates all the way up until failure. Again, a fault is not a failure. So if we are able to identify when and where a fault has occurred, it gives us time to do something about it. So this is all about, this is analogous to the term diagnosing or diagnosis. Diagnosis, in a medical and reliability engineering context, is working out what has happened, what has gone wrong, what is causing this disease or this leak in this pump. And so once we detect this fault, we're able to do something about it. And of course, fault isolation is a really useful element of maintenance as well. So we're all big on fault isolation. Now, some ways you can make fault isolation a thing is to include things like built-in testing or built-in self-testing or built-in test equipment, where your product, system, or service automatically looks internally, for example, every time it starts up, to see if everything is operating within specifications. And if it is, fantastic. But maybe if the output voltage is not where we'd like it to be, or there is excessive vibration, or the temperature exceeds something we'd usually expect when things are all right, then our built-in test, our built-in self-test, our built-in test equipment can say, hey, we have a problem. And again, our thing hasn't failed yet, but it gives us a chance to get ahead of the curve before failure occurs. Now, often we have software taking care of this, software dealing with this problem for us as well. But in the software domain, where the system is code, fault isolation is analogous to error handling. One of the biggest things that software, so one of the most useful things that software can do is make sure that it understands when an error has occurred. So there have been plenty of spacecraft, for example, which have happily made calculations and trajectories and flight controls based on software errors. And that means they impact the surface of Mars at a great rate of knots, or that means they try and do a 90-degree turn as they're taking off from planet Earth and unfortunately disintegrate. And these are real examples. The software created an error, and the onboard system wasn't aware that there was an error state and happily plowed into something that was very, very hard. So that's fault isolation. Now, another approach to tolerating faults, which a lot of textbooks and reliability engineers might argue is not true or classical fault tolerance, is proactive maintenance. Now, proactive maintenance is obviously very is related to fault isolation. Proactive maintenance is all about trying to identify when something's going wrong. We know about CBM, condition-based maintenance, or predictive maintenance, or prognostic health management, where we're trying to address faults before they become failures. So preventive maintenance is also an example of proactive maintenance, where we, at certain intervals, will dive into our system to take that gasket out and replace it with a brand new one, because we know it's towards the end of its useful life. The idea is that we're trying to get ahead of the curve. Again, we're trying to make sure that a fault isn't allowed to propagate to a failure event. Again, I'll emphasize that a lot of reliability engineers won't consider this to be fault tolerance, but I've included it here because if you don't think about proactive maintenance in the design process, then you miss golden opportunities to really optimize future maintenance regimes. One of my criticisms of many interpretations of RCM is that we wait until we design something before we think about maintenance. Now, I know that true RCM practitioners out there know that not to be the case. good reliability engineers know we need to think of maintenance in the design process. And for that reason, I like including proactive maintenance as a consideration in the fault tolerance body of discussion. So that's proactive maintenance. It's obviously very, well, it's related to fault isolation, working out if there's a problem. Then there's reversion. In fact, reversion has another name as well, which is derating. And the idea is that if our system is able to identify if there's a problem, as is the case for our aircraft engine, we limit the top speed of the engine or the number of RPMs, again called derating. And the reason we do that is because if we limit the stress, we limit the output, we can limit the activity, by extension, we're probably going to limit the amount of internal stresses as well. So if, for example, an engine can detect the cooling system isn't doing what it needs to do, well, it could put an RPM limiter on the engine itself, so it generates less heat that needs to be dissipated through our faulty coolant system, as opposed to allowing our driver to continue at top speed and seizing the engine. We're able to drive at a lower speed back to a maintenance facility, which is always a preferable outcome. So that's our fifth approach to tolerating faults, having some onboard system that can derate our system. And the last one is redundancy, which is the duplication of components or functions. And everyone should have an inherent idea of what redundancy is about. But redundancy is not as perfect or as ubiquitous as we sometimes assume it to be, because redundancy has problems. So in this case, we have worked really hard on our pump, and we just realized that we need to have two pumps because that's a more cost-effective approach to improving the reliability of our system than investing more resources into making a single pump more reliable. And the good thing about this sort of system as well is that if availability is important, we can service or maintain one pump while the other pump is happily pumping away. So there's lots of reasons why redundancy is really good, and there's lots of reasons why it's bad as well. It's not a cure-all for everything. So if we have a redundant system, sometimes if we're not on top of things, fault-tolerant components can hide faults occurring in other parts of the system. So if we have a two-pump redundant system, if one pump is struggling, because there's a second pump working, happily pumping away, we might not know that there is a problem with our allegedly redundant pump. And it's only when the primary pump fails that this problem surfaces. And of course, by then it's too late. So redundant components can fail without us knowing as well. And there are more components and isolation systems and containers to maintain when we have these pumps. So we need to have more piping for our pumps. We might need to install a valve. So just having redundancy adds complexity, which might negate all or some of the reliability improvement we're hoping to get. And of course, when we have more components, we have more weight and higher costs. And that might not be a big deal in, for example, a manufacturing plant where, of course, space is always a premium, but space is not the same. Space does not have the same premium that it does have for a smartphone, for example. We are really trying to push as many things as possible into a smartphone, and even though, yes, manufacturing plants will always complain about how much space things take up, it's not the same pressure. And so when all these things combine, we often get lazy. What do I mean by lazy? Well, sometimes we feel that if we have redundancy, we can use inferior parts of components. And there are certain certification exams out there where that is the correct answer to a question. And that's clearly not what redundancy was supposed to. That's clearly not a behaviour that redundancy was supposed to inspire. We can sometimes delay maintenance because we have this fuzzy feeling that everything's going to be okay because, well, we've got a redundant component, so we don't have to do maintenance straight away. And it means we stop thinking. Now, a very good example, or a very bad example, from whichever perspective you want to look at, of us stopping thinking happens in my Royal Australian Navy back in the day. So this is HMAS Canimbla, which was, turned out that it was frequently being put to sea with broken redundant systems. There was always pressure on engineering budgets. There was always pressure on downtime. The captains of these vessels and ships wanted to spend as much time at sea as possible. And so what was happening was that if they had, for example, 3 redundant components in the system, if one of them was working, they'd put to sea. And this affected the culture. This affected the general decision-making. And this approach to business spread across virtually all the fleets. And so, for example, this vessel here, which was supposed to be on standby to help in the event of a civilian emergency within Australia, turns out it wasn't able to support cyclone disaster relief up in far north Queensland when it was supposed to be available to do it. And when this thing happened, then a review and investigation into the state of naval vessels was instigated, and that review was not pretty. It found that culture was, maintenance culture, engineering culture, was essentially the root cause of these vessels not performing the way they needed to. And quite specifically, there is an assumption that if a ship was safe to sail, unless proven otherwise. So we could see that we're trying to push as much or squeeze as much out of our equipment as possible without investing the time and money that it needed to take to get those ships up into a seaworthy state. And we ended up having to spend a lot more money on average overall, because as opposed to preventing failures, we're having to throw money at crisis after full-blown failure, after very expensive breakdown, so on and so forth. So redundancy and fault tolerance can affect culture. But redundancy also has another problem, which is common cause failure. Now, common cause failure means that when we have, for example, 2 pumps, we typically assume that failure is independent. That means if one pump fails, it won't affect the state of the other pump. Problem with that is it doesn't always happen. So if one pump catches fire and that one pump is underneath another one, well, that second pump is going to potentially catch fire as well. And there's things like if there are common problems in the environment, if there's a restriction on the upstream pipe, well, of course, this is going to have inflow problems for both pumps. Now, if this accelerates failure, then we have a common cause failure event as well. If the shafts were installed by the same maintenance team, that maintenance team had the same potentially substandard training regime or training package, then the same installation error will exist for both pumps. We sometimes overlook things like power supply. I've seen many reliability block diagrams where we've had allegedly redundant systems that turned out to have a common cause failure as simple as a shared power supply. Again, similar to the installation issue, if we had the same maintenance regime, and that maintenance regime is not up to scratch like it was in the Royal Australian Navy, then this redundant configuration isn't redundant at all, because they are both going to fail in an accelerated fashion because neither of them is being maintained properly. So common cause failure is the enemy of redundancy, which is also one of the more common or more popular fault tolerant approaches. But what does common cause failure do in practice? Well, let's do some statistics. And I know everyone here loves statistics as much as the next person, but let's try and keep this as simple as possible. Now, let's just say we have done some reliability testing and we understand the time to failure of our single pump. This blue density curve, this blue bell curve, represents or explains to me the likelihood of our pump failing at a specific time to failure. And little golden nugget, little factoid, if you see a bell curve describe time to failure, you know by definition that that system is wearing out. Okay, so this is the bell curve that describes time to failure of our pump. Now, I can use this curve to work out, for example, how long it will take before my pump has 90% reliability. So if I had a fleet of 1,000 pumps at this point in time, as indicated on the screen, I would expect 900 of those pumps to still be working. I'd expect 10% of them to have failed, which is 100, but 900 to still be working. Now, if I add a single pump in redundancy, then the combined time to failure for my two pump redundant system, well, I have, one redundant pump system, I have two pumps in total. The time to failure density curve looks like this, and it's been pushed to the right. So the time by which I expect 10% of my redundant systems to fail is now this. It's 22% longer than if I had a single pump only. Now, if I add another redundant pump, so now I have two redundant pumps, the time it takes for me to expect 10% of my fleet to have failed increases by another 9%. So a key takeaway here is that the effect of redundancy diminishes for every redundant component you add in. But you can see here that increasing the time it takes for 10% of your fleet to fail by 22% is, in many cases, a really worthwhile benefit. But let's look at this case if we are focused on 5% of failures. What do I mean by that? Well, if we can see here that if we are, for example, focused on a warranty period where we have a warranty reliability requirement of 95%, implying a 5% failure probability, then our single redundant pump increases the time to until 5% of our fleet has failed by 26%. And adding a second pump increases that duration by another 10%. And these figures get more and more pronounced when we have smaller failure probability tolerances, or our reliability requirement increases. So, for example, if we are looking for the time by which only 1% of our pumps will have failed, so out of 1,000 pumps, 990 are still working by this point in time, adding a second pump increases that duration by 39%. Adding another pump after that increases that duration by another 13%. So this is a sort of really quick dabble into probability statistics to allow us to look at how common cause failure can potentially ruin our day. Now, so let's just say that 1 in every 10 failures has a common cause, and this is about right. We have found by rough experience over the years that about 1 in every 10 failures has a common cause. So what does that mean for our system where we can tolerate no more than 1% of our pumps failing? Well, what I'm going to do now is replace these red density curves, these red time to failure density curves, with green curves. And these green curves represent the change in our system reliability characteristics when we have a 1 in 10 common cause failure. Now, you might think that these green curves look very similar to those red curves. And those red curves assume that there's independent failure. Green curves say, hey, you know what? 1 in 10 times, both pumps are going to fail due to the same event. But let's look at what that means for our durations until 1% of our systems have failed. So where we might have previously calculated a 39% improvement in the time until 1% of our systems have failed, that is now back to 30%. So we are often caught out hoping that every single failure in our system is independent, but in practice, common cause failure can limit the improvement to reliability we expect to get when we have redundant systems. So redundancy, which is one of the most popular fault tolerance approaches, does have some hairs. So redundancy, I know we're talking about this a lot, but we just need to talk through it in great detail, to understand it thoroughly, I should say, before we think about using it to solve our reliability engineering endeavors. So we know that redundancy has a decreasing benefit for each additional redundant component. We also know that common cause failure diminishes the positive benefit of redundancy. But we also know there's an increasing benefit with a smaller number of initial failures. So if you have a very high reliability requirement, then redundancy has a huge impact on your overall system reliability performance. But this is all great for hardware. What about software? Because software has its own approach to redundancy. And software is often overlooked when it comes to reliability engineering. So why do we need to have a different approach for software when it comes to fault tolerance and redundancy in particular? Well, let's go back to our two-pump system and replace these two pumps with an algorithm. So let's just say we are trying to create a program which sorts numbers. And the idea of a sorting algorithm is that it takes a bunch of numbers, gets fed into our program, and out the other end, those numbers are ordered from lowest to smallest to highest. Now, this sorting algorithm here is what we call a bubble sort algorithm. And here is the code that I used to create this program. So how a bubble sort algorithm works is that it iteratively looks at pairs of numbers. So the first pair of numbers in this case is a 7 and a 3. And if those numbers are the wrong way around, it switches them. Then it looks at the next one. If it's not the wrong way around, it doesn't switch. And then it keeps going. It keeps going. Well, what will happen is if it goes back to the start, and that very first pair is in the correct order, so 3 is less than 7, it essentially puts this hypothetical check mark next to it. Then it goes to the next pair, and if that pair is in the wrong order, that check mark gets erased. But it keeps going through our numbers, and you can see that it keeps sorting, it keeps switching these numbers around. And it goes back to the start. We get our check mark, oh, another cross, and we keep going. And this bubble sort algorithm will keep doing this over and over again until we get to a situation where we have nothing but check marks. So here we go, have a check mark here, check mark there, check mark there, check mark there, check mark there, and huzzah, we have our final output, which is fantastic. So that's what a bubble sort algorithm does. So let's zoom in onto a particular line of code. In this case, what this code here is does is identify if a second number in a pair is higher than the other one. Sorry, if the first number in the pair, I should say, is higher than the second one. If that's the case, that's where we switch these numbers around. But let's just say there's a coding error, that instead of this greater than sign, we have an equals to sign, or equal sign, I should say. And that will ruin the day of our bubble sort algorithm. And what that means is that when we put it this algorithm back into our program, back into our code, the numbers that go in will essentially go through our program and remain unchanged. So in this case, this jumble of numbers gets fed into our program and gets spit out the other end. Now, the reason why this happened, even though we have redundant bubble sort algorithms, is because both bubble sort algorithms have the same fault. In a way, this is an extreme or ultimate example of common cause failure. If you have two identically defective codes, doesn't matter if one's in redundant configuration or not, they're both going to give you the same wrong output. So some smart people out there might be saying, you know what, let's get different code, because there's lots of different sorting algorithms out there. So let's replace the redundant program with this another program based on a shell sort algorithm. But there's another problem with this, and that is if these two programs give different outputs, how does a software program know which one to trust? It will at least know there's an error, but in this case, we want to have at least one interpretation of the output. So what we can do is add another program based on another software coding approach, in this case using the block sort algorithm. And once we have 3 programs all doing the same thing but using different methods, we can introduce a voter program. In this case, it's going to be a majority voter. The majority voter will say, hey, if 2 of my programs have the same outputs and the third one doesn't, I'm going to go with the 2 that are the same. I'm going to vote in the majority. And that will, it's incredibly unlikely that if we have 3 genuinely different approaches to software coding, that they will have exactly the same faults, or those faults will manifest in exactly the same way. So this is called N-version programming, where N refers to the number of programs we incorporate into our overall software program to achieve a certain outcome. And this is a really useful way of tolerating faults in the software domain. And of course, there's lots of other software approaches to tolerating faults, not least of which is good quality, well-commented, well-formatted coding, so that if someone needs to come into your code later on, they don't have to decipher equations that essentially mean nothing until you follow the logic. You can label and describe in your code what you've done as you've gone about it. That will make subsequent fault tolerance really, really easy. It allows people to go in and modify and update your code once they realize there's a weakness or there's an opportunity to improve it. So that's software. But of course, there is one further element for reliability engineers to consider, and that is us humans. We make errors all the time, and we are often the source of faults that systems need to tolerate. In 2009, Flight Air France 447 crashed in the Atlantic Ocean, and all occupants, all crew, all passengers unfortunately died. And there were a number of reasons for this crash occurring. Effectively, what happened was this aircraft was flying on autopilot quite happily, and then for whatever reason, there was potentially an airspeed indicator issue. The autopilot snapped out, and the pilots essentially put the aircraft in a stall configuration. They pulled the nose of the aircraft up, and they didn't realize they were in a stall condition. And the aircraft stalled and was going essentially straight down, and it pancaked on the Atlantic Ocean surface, killing all on board. Now, one of the contributing factors, or factors that was at least at play, was the layout of the cockpit of the Airbus 330. So here is a picture of it here, and it has lots of instrumentation. There's lots of things, or screens, and all sorts of different buttons. The thing I want you to notice, though, is the side sticks, which are, in this case, look essentially like joysticks, computer controller joysticks. And what that meant was that the co-pilot could pull hard back on one joystick, while the pilot to his left could be pushing forward on the other joystick. And this would introduce different inputs to the computer, the onboard computer, which is controlling the aircraft. And in this case, this is exactly what happened. The pilot realized it was a stall situation and was pushing forward on his joystick. The co-pilot, for whatever reason, was pulling back, and we're not entirely sure why. Because perhaps he was panicking a little bit, and he was trying to gain altitude, because at this stage, the aircraft was plummeting to Earth. And with these mixed inputs, the computer essentially had to make a choice, and it went with the controller that was essentially asking the plane to pull the nose up. So the pilot believed the nose was being forced down, and still couldn't understand why there's a stall condition. And when the captain was awoken and he came forward, it was only, I think, the last 15 seconds, when he realized what was going on, then he instructed the co-pilot to push the nose down so they could get airspeed and get out of the stall condition, but it was too late at that stage. Now compare this cockpit with another cockpit. Now again, there's lots of buttons, lots of instruments, lots of things going on. But the thing I want you to notice in this configuration are these control yokes. Now these control yokes essentially provide the same input interface or user interface as those side-stick joysticks. But the other thing about control yokes is that they are very visible. They're connected and they provide tactile feedback. It is physically impossible for a co-pilot to push his or her control yoke forward while the other one is pulling it back, because they are connected. Wherever one goes, the other goes. And even if they weren't connected, they are very, very visible. So you could see really easily if one pilot was pushing forward or the other pilot was pulling back. So this is an example of a cockpit configuration which is inherently fault tolerant because human beings make errors, which then become faults the systems have to overcome. So we can often design really reliable, really wonderful systems and forget about the human element. And that human element is one of the biggest sources of faults going around. So fault tolerance. Fault tolerance is the ability of a system to not fail with the existence of faults. And we've covered a little bit of fault tolerance today. We've covered, I suppose, a very high level, relatively exhaustive summary at the high level of what fault tolerance is all about. There's 6 approaches which start with variability control, move all the way up to redundancy. And we try and create systems which tolerate faults once we've exhausted all economic or efficient ways of making or baking reliability into our components. And it all comes back to this thing I like calling the reliability mindset. The reliability mindset comprises of value, the language that us reliability engineers use, and the methods that leverage that common language that allow us to work together. So in previous lessons or previous webinars, I use this tree to represent the tree of failure, the roots representing root causes of failures, and those horrible apples at the top representing failures, failure events. And we want to create reliable systems which minimize the occurrence of these apples, which limit the size of these apples when they do occur. But if we can't do that anymore, we, in a way, want to cheat with fault tolerance. We want to create failures which require more than one fault state to occur or fault condition to occur. In a way, we're breaking down apples into pieces so that for our failure to have occurred, we need both pieces of the apple to manifest themselves. That's what fault tolerance is all about. There's always a time where it's more feasible or cheaper to start tolerating faults. And beyond that, fault tolerance is a useful approach to making robust designs. That the Airbus 330 cockpit and any other cockpit which has a control yoke could be technically, mechanically, from a strict engineering perspective, as reliable as each other. But one cockpit can tolerate human faults way more than the other. So we should always be thinking about how to tolerate faults to make robust and reliable systems. So on that note, are there any questions? So I hear from Ahmed that he understands the recording and a certificate of attendance will be sent later. Kindly confirm. Fred can jump in here, but I don't believe we're in the habit of providing certificates of attendance for webinars. This is supposed to be this is not a formal training program. Obviously, we do lots of training, lots of learning, but as far as I'm aware, there's no certificate associated with webinars. But that said, Fred can either confirm or correct one way or another.
Yep. I believe if the system is set up right with the Zoom setup, you'll receive a thanks for attending notice. That, along with the abstract page, works if you're trying to claim points for a certification, recertification points, or whatever those things are called. That typically works. And I'll have to double check. I haven't run in that question for a while, so I'm not really sure. So let me go look.
Awesome, thank you. All right, so Keith asked the question, can I define common cause failures again? Okay, so I'll try and explain it from a different perspective. Independent failures are failures that occur where the failure state of any other component doesn't affect the probability of failure for this component. So that means that if you have 2 pumps, then the state of the other pump, the probability of failure of the other pump, the failed state of the other pump won't affect the probability of this pump failing. So that's independent failure events. Anything besides that, any variation to that scenario involves common cause failure. So common cause failure for those two pumps could emanate from the environment. So, for example, if both pumps are in an environmentally controlled chamber and that air conditioner cuts out, all of a sudden the humidity and temperature goes through the roof, then if those pumps fail because of accelerated temperature degradation, then those pumps have failed due to a common cause, which was an environmentally based common cause. If those two pumps fail because they are serviced by the same maintenance team, and that maintenance team is not trained correctly or otherwise incompetent, those two pumps have failed from a common cause, which, even though that you don't often include maintenance teams in the environment definition, that's still an environmental based common cause. Another common cause is where the failure event of one pump initiates the failure of the other. So, for example, if a pump flat out explodes and shrapnel goes flying through the air, and that shrapnel then damages the other pump, and that pump then starts to fail within the next hour or so, then we also have another example of common cause where the cause is embedded in the failure event of another pump. Then there's nuances to that. So, for example, if you have a load sharing system, the load sharing system in a pump scenario might be a system where, for example, we need to have a systemic flow rate of 75 gallons per minute. And we might have two pumps arranged seemingly in parallel to do that. So for the system to meet its requirements, if both pumps are working normally, then both pumps need to pump 37.5 gallons per minute to meet the system requirement. Now, if one of those pumps fails, then the other pump needs to increase its flow throughput from 37.5 gallons per minute to 75 gallons per minute. Now, that second pump might still be able to do that, but it's out of that high reliability zone. And so any failures that are accelerated by that condition are also called common cause failures, because there is a single cause. The cause that to result in that first pump failing then went on to influence the second pump failing. So that's an example of, hopefully that explanation has helped you get on top of common cause failures again, Keith. If that's not the case, feel free to throw a comment in there and I'll have another go. Okay, Maximilian, how do we test if our system is robust to faults? So if we label the system in a way that mandates that it needs to be regularly lubricated, it is conceivable that lubrication could be forgotten, human error as discussed. How do I create a test regime that accounts for this occurrence? It seems like my quantity for test samples is ever increasing. Maybe that is the real problem. So I don't understand how you're going to test for human error in this context. For example, you could be referring to a scenario where humans, your maintenance team, are tested or their work is inspected after they do something, which has happened in plants from time to time, where some sort of, perhaps the foreman or the supervisor will go and look at what the maintenance team have done and ensure they're up to speed. That's one way of testing the efficacy of your humans, but I'm not entirely sure what you're getting at in regard to testing. Now, a more robust approach could be having having some sort of lubricant contamination sensor. So that you have a sensor on or inside the sump of that engine or whatever it is that's having its oil change, so that if the contaminants exceed a certain level, an alarm goes off. That is often more resilient to faults than humans that you might not have a lot of trust in for whatever reason. Regardless of if the humans go and do what they're supposed to do, they change the oil and they don't do a good job, you still have that onboard sensor that's going to detect if the contaminants are exceeding a certain threshold. The other good thing about those sort of sensors is that they can help you identify precursors to things like bearing failures, and because bearings sometimes eject a material when they're on the way out. So if you want to try and test how robust your system is, if you try to test if your system is robust to faults, it's a very broad question. Software teams, for example, they use this thing called software fault injection. And the software fault injection does a couple of things. It essentially tests if how the system responds to those injected faults, but it also tests your fault detection process. So if you inject 80 faults into your software code and your software detection system, your beta testing program, your alpha testing program, whatever review system you have, only identifies 5 of them, then you know that you could expect that at 75 out of 80 defects, I should have used 100, that'd have been an easier number to derive a percentage from. But anyway, I'm stuck with 80. If you have 75 out of 80, which is, I think that's not 95, it's a bit less than 95%. That means you still have the overwhelming majority of faults floating around your system that were inadvertently put in there by those software engineers when they first coded your system. So there are lots of different ways of testing if your system is robust to faults. One approach I'll go back to is that Netflix Chaos Gorilla, Chaos Monkey approach, where they continually throw curveballs at your system. They do this in a way which is very controlled though. So if you want to make sure your system is robust, you can do it either in your mind, through design, or through those tests that our Simian Army team came up with at the very, very start. It's all about understanding what you need to do. I also might plug a particular statistic here. Carl Carlson, our friend, often throws around this statistic as well, that about 50% of failures occur at interfaces. That is where components interact with each other. And that is one of the most common sources of faults. So FMEA, which is conducted really well, where you have a facilitator who really focuses on interface functions, is a great way of introducing robustness into your system. So I suppose there's tons of answers here, tons of approaches for incorporating robustness and fault tolerance into your system. HALT's another great example, because HALT essentially exposes your system to all sorts of stresses, and you keep accelerating those stresses or increasing those stresses in a scientific way until your system can't tolerate it anymore. And once you do that, you work out what went wrong, improve the design of the system, and keep going. So for me to be able to answer that question, I'd probably need a very specific scenario, which I'm more than happy to talk about if you have one, either in this window of opportunity or separately later on. Any more comments or questions? Thank you, Keith. Much appreciated. I guess that means Keith has no more questions. Anybody else got any questions? We might give you guys another 30 seconds to a minute or so to throw any issues my way. More than happy to talk about them at length. And of course, any plans of a webinar on lubrication? Not at this stage, Fred. That's a good idea, though. So maybe we can add that to the list of webinars. I do believe Terry Harris does lubrication, Fred. Is that right?
Yes, he does.
Yeah, so Ascendo does have webinars which tackle the topic of lubrication as well. So if you go to ascendoreliability.com, you should be able to see what offerings our colleague Terry Harris has. No worries. Well, if that's it, ladies and gentlemen, thank you very much for your time again. It's always a pleasure talking to you guys. Thanks for your feedback. Again, you got my contact details. If you do want to have a conversation about this or any other reliability engineering topic, and I know Fred's the same, feel free to reach out. We'll give you an answer, regardless of how good a quality that answer is or not. You will get an answer, or inspire a longer conversation to help you get to where you need to be. But beyond that, thanks again for your time today. Don't forget, you've got a handbook which has all this information. This webinar is recorded, so you can come back to it whenever you want. Beyond that, have a happy Tuesday from wherever you are across the world.